Hello everyone, so this video presents our PPL3 project on deepfake image detection using a fuzzy logic systems. So our system evaluates visual inconsistency in image and produce a risk-based output rather than a binary decisions. In this presentation, I'll explain the fuzzy variables, membership functions, rule-based, live fuzzy inference, and critical analysis of the system behavior. So what you need to know about our system, basically, our system uses two input variables. First, skin texture abnormality and eye reflection inconsistency. Both are defined within a domain of 0 to 10. So the output variable is deepfake risk level, also in the range of 0 to 10. So basically, these features are chosen because the deepfake image often show oblismal skin textures and inconsistent eye reflection due to artificial rendering. So the equation is why fuzzy logic. Visual features in deepfake detections are not binary. An image may contain both genuine and manipulated characteristics. Fuzzy logic is stable because it allows partial evidence, handles conflicting indicators, and produces credible risk-based decision instead of strict yes or no outputs. So next, we move on to membership function designs. So in membership function design, each variable is represented using three linguistic terms, which is low, medium, and high. Basically, we use trapezoidal membership function with overlapping regions to allow smooth transition between the categories. So this overlap is very important because a single feature's value can partially belong to more than one set, reflecting uncertainty in real image analysis.
For this part, I will show fuzzy plots for at least 2 input and 1 output, and each variable will have at least 3 membership variables. Since this is about deepfake image detection, the fuzzy system estimates an overall deepfake risk level based on 2 visual cues. The first one is skin texture abnormality, second one is eye reflection inconsistency, and the output is deepfake risk level. All of my fuzzy variable use the same domain from 0 to 10. 0 means the feature is basically not present or it looks normal. 10 means the feature is very strong or very suspicious. So if skin texture abnormality is near 0, the skin looks natural. If it's near 10, the skin looks very unnatural and is likely deepfake. Each input and output has 3 linguistic levels, which is low, medium, and high. We are using this because in real checking, we don't usually say it is fake or it is real immediately. There are degrees. So fuzzy sets let us represent that gradual uncertainty. Now we will show the membership function live. So here's the plot. Okay, for input 1, skin texture abnormality. We can see 3 membership functions, low, medium, high, and they are trapezoidal. Low is defined by 0, 0 to 4. That means from 0 to 2, it is strongly low. Membership is near 1. And then it gradually decreases until around 4. For medium, it is 3, 4, 6, 7. So medium start rising around 3. It becomes fully medium between 4 and 6, and then it will drop after 6 until around 7. And lastly, high, it is 6, 8, 10, 10. So high start increasing around 6. And then it will become strongly high around 8. And it will stay high until 10. The key point here is the overlap. For example, around 4 to 6, we can see the value can be partly medium but also slightly low or starting to become high, depending on where it is. That overlap is how fuzzy logic avoids sharp cutoff. Okay, second one is eye reflection inconsistency. We use the same membership design, low, medium, high, with the same trapezoid points. This means low means the reflection looks consistent and natural. High means the reflection looks suspicious, like the lightning doesn't match between eyes or the reflection looks artificial. We keep the same shape and threshold because both input share the same scoring scale from 0 to 10. So the fuzzy interpretation stay consistent across the features. And lastly, the output, which is deepfake risk level, also from 0 to 10 and also with low, medium, and high. Low risk means the system really believes the image is likely genuine. Medium means it is uncertain or it gives mixed signals. And lastly, high means strong deepfake indicator.
So for the fuzzy rule-based part, for the rule 1, which is strong deepfake indicators, it will happen when both skin texture abnormality and eye reflection inconsistency are high. So it will indicate strong visual manipulation, and therefore the system will assign a high deepfake risk level. For the rule 2, basically strong genuine indicators, when both features are low and the image will show the natural characteristic. So the system will interpret this as a low deepfake risk and indicating a likely genuine image. While in moderate or uncertain in rule 3, when both features are at medium level, the evidence is unclear. This results in a medium deepfake risk representing uncertainty rather than defined conclusion. So what happened in conflicting visual evidence? In rule 4, this rule will represent conflicting visual evidence where one feature suggests manipulation while the other appears natural. Instead of forcing a high or a low decision, the system outputs a medium risk level. So these rules allows the system to handle both clear and conflicting evidence, which is common in real deepfake image.
Sistem ini menggunakan Mamdani Fuzzy Inference System dengan 2 input iaitu skin texture abnormality dan eye reflection inconsistency dan 1 output iaitu deepfake risk level. Operator N yang digunakan adalah min dan defuzzification menggunakan kaedah centroid. So untuk test case 1, input ialah skin texture abnormality adalah 8 dan eye reflection inconsistency adalah 9. Dalam kes ni, hanya rule satu yang valid, iaitu if skin texture is high and eye reflection is high dan defect risk level is high. Rule ni valid sebab kedua-dua input jatuh dalam kategori high membership dengan operator min. Firing string adalah kira-kira 0.8. Selepas aggregation dan centroid dephasization, sistem menghasilkan high crispy output yang menunjukkan defect risk yang tinggi. Manakala untuk test case 2, input ialah skin texture abnormality equal to 2 dan eye reflection inconsistency equal to 1. Hanya rule 3 yang valid, iaitu if skin texture is low and eye reflection is low, then defect risk level is low. Rule ni valid sebab kedua input berada dalam kategori low membership. Firing string kira-kira 0.8 dan hasil dephasization adalah low crispy output yang menunjukkan defect risk yang rendah. Untuk test case 3, input skin texture abnormality equal to 5 dan eye reflection inconsistency equal to 5. Hanya rule 2 yang valid, iaitu if skin texture is medium and eye reflection is medium, then the effect risk level is medium. Kedua-dua input berada tepat pada puncak fungsi medium membership. Jadi, firing string akan jadi 1.0. Central dephasization menghasilkan medium crispy output yang menunjukkan defect risk sederhana. So, kesimpulannya, sistem ni berjaya menghasilkan crispy defect risk level untuk setiap test case. Input yang tinggi akan menghasilkan high risk, input yang rendah akan menghasilkan low risk dan input sederhana akan menghasilkan medium risk. Output ni clearly menunjukkan keputusan akhir tahap deepfake berdasarkan input yang dimasukkan. Untuk manual calculation ni saya akan ambil test case 1. So, input skin texture abnormality equal to 8 dan eye reflection inconsistency equal to 9. Ia mengaktifkan rule height and height, so output fuzzy set ialah height 6, 8, 10, 10. Daripada fuzzification, membership untuk 8 ialah 1.0 dan untuk 9 ialah 0.75. Jadi rule firing string W equal to 0.75. Kita clip output fuzzy set pada nilai ini dan ambil titik penting, iaitu 6, 8, 9, 10 dengan membership masing-masing 0, 0.75, 0.75, 0.75. Using center of gravity method, kita kira jumlah setiap titik X di dalam dengan membershipnya dibahagikan dengan jumlah semua membership. Ia akan menghasilkan COG equal to 8.44. Method min menggunakan central high fuzzy set Z equal to 8.2 menghasilkan WM equal to 8.2. Manakala min of maxima ambil peak dominant pada S equal to 9. Jadi min of maxima equal to 9.0. Perbezaan ni jadi sebab manual calculation guna discrete points dan pilih satu peak dominant. Tapi Python skfuzzy.defast compute continuous integral atas 1000 point dan purata semua X pada plateau maksimum. Ia akan menghasilkan COG lebih kurang 8.35 dan min of maximum 8.75. Walaupun numerik sedikit lain, kedudukannya jelas menunjukkan output berada dalam high risk, membuktikan sistem fuzzy berfungsi dengan konsisten.
This is a step point, the 10-point stress test. So I will first execute 10 inputs live from 00 to 99, and then I will show the crypt outputs and the resulting 10-point curve. These printed values are the 10 crypt outputs produced by the fuzzy inference system. So here is the baseline graph. This graph shows the baseline 10-point curve. We can clearly see a plateau behavior in multiple regions. First, we can see a low risk plateau from input 0 to 2, and then a medium risk plateau from 4 to 6, and it is followed by a sharp jump into the high risk region. The anomaly that we identify here is the medium risk plateau between input value 4 and 6, where we can see an increase in input severity does not significantly change the output. Step 2, hypothesis. Based purely on the curve behavior, our hypothesis is that the medium rule will dominate strongly across this region, and it will cause defuzzified centroid to remain stable even as input increase. Once the input crosses the membership boundary, dominance shift to the high risk rule, resulting in a sudden jump. Okay, so for step 3, modify one MF parameter. Now I'll modify one membership function parameter. So here we are adjusting the output membership function for the medium deepfake risk level. We're going to change it from 3467 to 3457. This single change narrowed the medium region, meaning that the system should leave medium risk earlier. And then we reboot the rule-based in control system, so the modified membership function is applied. I will now rerun the exact same 10 input from 00 to 99. And then this is a new curve after the membership function change. Okay, this is the comparison graph. This comparison shows before versus after behavior. From this graph, we can see that the medium plateau is slightly lowered after the change. The system transitions out of medium risk is earlier, and the output around input 4 to 6 is reduced compared to the baseline. In the context of deepfake detection, this change is significant. The medium risk plateau represents borderline or subtle manipulation, things like male skin smoothing or slightly inconsistent eye reflection. So when we narrow the medium membership function, the system becomes less tolerant of ambiguity and escalate risk more decisively. This can improve sensitivity to borderline deepfakes. Okay, it will reduce the chance that subtly manipulated images remain classified as medium risk for too long. Overall, this demonstration shows how a single membership function parameter can directly influence system sensitivity and decision behavior in a real-world deepfake detection context.
For high-res images, the score is high, which usually means the image is manipulated or a deepfake. Fuzzy logic helps us detect these cases accurately. Medium-risk scores are less clear. Here the result is uncertain, so it needs another check or a human review. Using partial membership, fuzzy logic can handle this uncertainty without forcing a yes or no decision.